Showing what the final product at the end of the day of my asynchronous online lectures look like. First, I come here and I set the speed to 4 times, because otherwise this video would last an hour and 20 minutes. So the online lecture, in the end of the day, it's a movie. It has contributions from all the class, and it happens like this. I am writing on the slides while the audio, you can hear me in the background speaking in this class, and this icon here on the left, it means these my contributions to this class. So it will take some time before you see the students' contributions. At this point, I am just recalling previous concepts from past lectures that will be used today. And let's skip this part. So you see this part, this slide, which would be like a scene of a movie, it consists of many pieces, in this case 3 pieces. So let's skip to the next slide. Well, this one is just a title, and now again some explanation by myself. What you can see here on the top right is the name of the person making the contribution, and so far it is only me. And on the left it is my contribution. So when I hold the mouse over here, you see my name on the top right. And now I can So here's when it starts. I'm proposing asking students to do a simple exercise as I warm up. And the students are supposed to contribute the solution, and here's a student explaining the solution to the problem. The student chose a format which is writing first on a piece of paper. This is a very popular format in my class. So writing on a piece of paper first, and then explaining it, pointing with a pen or some other object while filming it, and explaining the solution to the other students. And after that, another student making a constructive criticism to the solution presented by the classmate, which means pointing out whether it's correct or not, whether it's complete, and any important omission that there is in the argument. So here again, as you can see at the bottom of the slide, I asked for one video solution. So I have previously discussed with the students my expectations, and assigned a group of students that are supposed to contribute in today's lecture, and the number of students that are supposed to contribute roughly matches the total number of videos that I am requesting. And I'm requesting a little more, so students have some flexibility, and it covers for any misunderstanding or eventual mistake. So here I'm changing the topic. I'm changing to orthonormal diagonalizable, giving the definition. Let's skip to the next slide. Okay, and I'm stating the theorem. So students could have asked a question here. They did not ask the question, but sometimes they do. So I'm stating the theorem, then I'll state the real version, of course. And this is a very special lecture. It does not have many different propositions and theorems. It has 2 big theorems that one can split their proof into small lemmas, and this is what I did to the possible extent. So okay, this student chose a format which is he's writing on a whiteboard and explaining the solution. So he's like a teacher writing his solution on the board and explaining it to the other students and filming himself. And once he's done with his proof, another student will comment, will say it's concise, it's complete, it's correct, nice proof, and if you, I can make a suggestion for you to improve in the future, and then they make a suggestion of what aspect of the presentation could have been better and can be made better in the future. And you see here on the left the story. Now the slides start to have a story, it's a thread. There's my audio at the beginning. So here, let's look at this. Let's look at this slide. There's my audio at the beginning. It's represented by a big square. And then there are two other threads. The threads, they start with a square. And they are followed by these little circles here. So which means it's not chronologically ordered. Maybe this reply to this video was posted after this video. But when the final version of the lecture, they are structured by threads. So it is something that makes more sense. You don't have to keep referring back to something that appeared before in time. And so there are three levels of organization of this sequence of contributions that you see. One is the slides, and you can see at the top here that there are 25 slides in this lecture. We are already in the slide 13. The second level is the squares, which is the posts that people make in one slide, and then the replies to the posts that appear right after the post. So in the end of the day, after all the students made their contribution, I come and I make my own comment, and you see my own comment, it appears at a precise position in this sequence because I go following the thread. So here another student who chooses the solution of writing on a paper and presenting the solution. Whereas the previous one had written something on a paper, taken a picture, processed it, and now is showing it on the computer. Let's move forward. Next slide. So here will be the only if part of a complex spectral theorem, and I asked two students to present a video, and if we scroll down here you see there is one student presented a video, a student made a comment, another student made a comment, I made two comments myself, and then there is another video solution also proving this part of the implication, and then the student made a comment, the student who made the original post replies to the comment, and I make a comment in the end. Okay. So now you see that this student, she also chose to write on a paper and explain the proof. If we move forward here, then there is this student made an audio comment. I disabled audio, but sometimes students manage to post audios anyway. I disabled audio because I think it gives a nice touch, human touch to the lecture, to see students' faces when they are making the comments, and the classmates they can see their classmates. So, and here is, I made a video comment exceptionally. I also made a video comment myself here. And here another student who writes on a notepad and then explains the proof. So let's move to the next slide. I'm moving because I want to keep this video short, of course, but in principle, if you just press play once, you can watch the whole lecture in the correct speed. So here we are on the if part of the real spectral theorem. So I say some words about it, and then I'm asking one student to show a proof, because of course this is an easier exercise. So the student shows the proof. Let me skip the proof, and then another student makes a comment saying that the proof could be simplified in a certain part. So here's when the other student is making a comment, and this one I also made a video comment myself to explain which parts can be simplified and why this proof actually is simpler than it seemed at first. This is exceptional. I normally don't make video comments, but this lecture was a very special one in the sense that too many subtle arguments, one after the other, that together build the spectral theorem. Okay, here I'm stating existence of eigenvalues, and that's a surprise in the end of the lecture that I am making the proof. Once students have proved a few lemmas about it, lemmas about irreducible quadratic factors. And this is the second ingredient in the proof of the real spectral theorem, together with existence of eigenvalues. So in order to apply a dimension reduction argument, you find an eigenvalue and then you consider the orthogonal space, orthogonal to the eigenspace spanned by that eigenvalue. And so I'm stating this, but not yet the proof, because the proof is done in several steps. And I'm moving directly to the part where we use those two lemmas to prove the real spectral theorems. This would be the high point of the lecture. I asked two students to post a proof, and I'm explaining how it can be done. So here's one student presenting a proof written on a paper, then scanned, and now he's using the mouse in his screen. He's doing a screencast using the mouse to point out the part that he's explaining. Another student, as usual, making a comment about it. And after the comment of that student, I am making a video comment myself. Oh no, I'm making a written comment saying how the proof could have been more abstract. And here is another student who chose the solution of a tablet. She's making a screencast of a tablet. She wrote the proof completely beforehand, and now she's just using a different color to add and highlight and add comments and remarks to the proof while recording the screen of her tablet and speaking, and then she uploads this video. This is a very high quality solution, so this is the format this student chose. And once the student is done with the proof, as usual, there will be another student making a comment. So of course the solution, the format and the dynamics is determined by the number of students in the class. So once I decided what amount of material is reasonable for one lecture, then I ask contribution of half of my students to make a video and the other half to make a comment. If I had more students, I would have made the division differently. If I had fewer students, I would have made the division differently as well. So now we are proving that second lemma, the one about invariant subspaces. We are making it split into three parts. So here's a student who wrote on a paper, and I was holding the camera very static while explaining the proof. Let us move forward. So another student who is doing a screencast of a tablet. So she's writing on a tablet. It looks like a tablet. She wrote the solution beforehand, and now she's just highlighting pieces of it while she explains. So this is a very clean and short and concise proof. No student made comments, so I'm making the comment. And here's another proof by another student who wrote it beforehand on a paper, processed it, and now is highlighting what is the proof, and the student is explaining it in the background. And now let's skip this part as well, and then we're going towards the end. So students are proving that irreducible quadratic factors, that's a polynomial like this that can't be further factorized over the reals. If you apply that polynomial to a self-adjoint operator, the result is an invertible operator. And so this is a classical lemma used to prove that self-adjoint operators must have an eigenvalue, and so the students are proving it here. So here's one student, has this very high quality format for presenting solution. The student is doing a screencast of a tablet using some efficient software for handwriting, and now the student is explaining his proof orally while highlighting parts of the tablet. And after that, the student posts a video making some small addendum to the solution, an audio. The student posts an audio making some addendum to the solution. Another student making a comment. I'm myself making a comment in the end. And another student providing a similar proof but using a completely different format, written on a paper as usual. And then here in the last slide, I posted myself the video of the proof of existence of eigenvalues. You can see this video on YouTube, so of course I'm not going to spend time here on my own video. So this is also a screencast of a tablet. So I'm using an app for handwriting, which also includes this laser option here, so I can highlight what I wrote and the highlighting disappears afterwards. So I'm explaining the proof. Again, this proof is on YouTube if you want. So I'm explaining the proof here, and there was a lot of questions. There was a student who was questioning one part of the proof where I went a bit too fast and didn't quite explain how I'm using the previous lemma, and basically why this is an irreducible factor. So students sent an audio saying precisely at 7 minutes of your audio, of your video, I don't understand that part. And the nice thing is I didn't do anything about it. Another student came and posted an answer to his classmate explaining exactly which part of, so he's filming the screen of the computer and then filming something he had written beforehand on the paper, just to explain to his classmates why we can apply how we can apply the previous lemma in the middle of this argument. And once this student is done, the other student posts an audio saying, "Thank you very much, it's absolutely clear now." So this was an amazing discussion. So in the end I come here and acknowledge that my proof was not succinct enough. So I hope this inspires people on how we can make a lecture online based on interaction rather than just delivering content.